Hello, this is Jack Jackson. In this video, in this section, we'll be covering a one-sample confidence interval for variances and standard deviations, and hypothesis test also for this. So we now have all the pieces, since we know about a chi-squared distribution, to use it to make confidence intervals and hypothesis tests. So we'll start with confidence intervals. First, note that taking the reciprocal of both sides of an inequality reverses the direction of the inequality. So, for example, if you have, at least if you have positive numbers here, so if you have a and b are both positive numbers, and we have 1 over a is less than b, then multiplying both sides by a cancels the a out on the left, puts the a on the right. Then divide both sides by b. We get to here, so 1 over b is less than a, so a is greater than 1 over b. So reciprocaling both sides reverses the direction of inequality. So that's going to show up here in just a minute. Now what we want is an interval where the probability of the test statistic is between the two bounds, and that has a confidence level of 1 minus alpha. So our test statistic is our chi-square value. So we want our chi-square test statistic to be between two bounds, chi-square lower and a chi-square upper. Now the chi-square lower, we want the probability less than that to be alpha over 2. So that's an inverse chi-square of alpha over 2 with whatever our degrees of freedom. Of course, alpha over 2 is 1 minus the confidence level divided by 2. So you could do it that way as well. The chi-square at the upper end is going to have alpha over 2 to the right, so it'll have 1 minus alpha over 2 to the left. As we've seen several times, another way to get 1 minus alpha over 2 is 1 plus the confidence level divided by 2. So if you know your confidence level, you can do an inverse chi-square 1 minus confidence level, then divide by 2, and an inverse chi-square 1 plus confidence level divided by 2, both with the degrees of freedom, which are 1 minus, or sample size minus 1. Okay. So let's look at a little algebra here. We want chi-square test statistic be between this chi-square lower and this chi-square upper as defined on the previous slide. Well, our chi-square test statistic we know is n minus 1 times s squared over sigma squared. Remember, s is the sample standard deviation and sigma is the population standard deviation. N is the sample size. So n minus 1 is the degrees of freedom. We're going to solve this where the population parameter sigma square, the variance, is in the middle. So what we're going to do is we're going to reciprocal everything, and that's going to give us 1 over chi square lower. Going to put the sigma square in the top, the n minus 1 times s squared in the bottom, and it's going to flip this one over as well. But when we do that, it switches from all less thans to all greater thans. Now I'm just going to multiply all three sides by an n minus 1 and an s squared to cancel this out to get sigma by itself. That puts an n minus 1 times s squared in the numerator here and here. So we get sigmas between these two. If we write it in the normal order, lowest, middle, highest, and use less thans, we get this equation right here, inequality right here. N minus 1 times s squared over chi square upper is less than sigma square, which is less than n minus 1 times s squared over chi square lower. And so this gives us a confidence interval. But notice that you use the chi square upper value for the lower limit of your lower end of your confidence interval. Use chi square lower on the upper end of your confidence interval because they're in the denominator. That reciprocal just kind of switches things around. Now, once again, chi square lower is inverse chi square of alpha over 2 times with your degrees of freedom, which is n minus 1. Okay. In fact, let me do this. I've actually rewritten that with degrees of freedom now replaced by n minus 1. So you're starting with the sample size and the confidence level. So if you want to think of this last one here, is what you do. You do an inverse chi square 1 minus confidence level divided by 2, and then n minus 1 for your degrees of freedom. And then you do an inverse chi square of 1 plus confidence level divided by 2 for n minus 1. This one will be the higher one, will be this one here. The higher one goes in the denominator in the first part, and the lower one goes in the denominator for the second part. And then your sigma square then goes from n minus 1 s square over that chi-square upper up to n minus 1 times s square over the chi-square lower. Or if you do this in terms of the sigmas, then you just basically square root everything. So sigma is between s times the square root of n minus 1 over chi-square upper up to s times the square root of n minus 1 over chi-square lower. So one thing you should note is that this confidence interval has a little different form than the confidence intervals for means and proportions. The confidence intervals for means and proportions had the form sample statistic minus e to sample statistic plus e, like x bar minus e to x bar plus e, or p hat minus e to p hat plus e. For confidence intervals for variances and standard deviations, we don't add and subtract from the sample statistics. Instead, we multiply the sample statistic by two values. So we take the, for example, for standard deviations, we take the standard deviation of the sample and multiply it by something here and multiply it by something here. We're not adding and subtracting, or not adding two values, a positive and a negative values. We're actually multiplying it by two values. Okay, and it turns out that when you do this, the interval will always contain the sample statistic, but unlike the means and proportions, the sample statistic will most likely not be at the midpoint of this interval, and that's due to the skewed nature of the chi-squared distribution. But anyway, this is basically how we go about constructing a confidence interval. So let's look at an example. A company is manufacturing a part and is measuring the diameter of the part. Assume that the diameters of individual parts are distributed normally. By the way, that's very important that for this technique that we're showing you here to work, the individual parts have to be distributed normally. Normally, the individual things have to have a normal distribution. It's not enough that the distribution of sample means be normal. So it's a little stricter, actually quite a bit stricter restriction than we had before when we were testing proportions and means and building confidence intervals for them. They take a sample of 20 parts and compute a standard deviation of the diameters of the parts is 0.02 centimeters. Compute a 95% confidence interval for the population standard deviation of the diameter of these parts. Well, notice if n is 20, the degrees of freedom is n minus 1, which is 19. S is 0.02. The confidence level is 95%, so the remaining 5% is split evenly. It's to 0.025 below the lower limit, lower chi-square lower, and 0.025 above the upper chi-square upper. So that's 0.975 below U. So we use these levels to compute the critical chi-square values. We could have gotten the same thing by doing 1 minus confidence level divided by 2 would have given us the 0.025. 1 plus confidence level divided by 2 would have given us the 0.975. So anyway, we can do that. We could graph the chi-square CDF and graph those two horizontal lines, calculate the intersections, and as we find them, say this one here, we do it first, calculate that intersection. As soon as we're done from here, that will be X at the moment. So go to the home screen, say quit, X stores U, and then we can calculate the lower one. Here's the lower one. The upper one was actually first, and there's the lower one, and then store that. Looks like I actually did the lower one first here, the upper one here. This 42 point something is left over from another problem. All right, so we just got rid of that extra stuff there, and now it looks a little bit better now. Now, of course, you can do it this way no matter what, but if you have my inverse chi-square program, then there's an easier way. Or if you have a TI Inspire, I believe an inverse chi-square is built in, and so you could use that. So if you have that, you can do an inverse chi-square program. It asks for the left probability. Again, put in the 0.025. and put in degrees of freedom as 19, then that's our lower, our chi-square lower. I could take that number and maybe store that as L, like I did over here. And then I run the program again to get the other one. The left probability below the upper one is 0.975, again 19 degrees of freedom. And there's our upper one, which I could store as U again if I wanted to, like this screen over here. All right, now we have everything we need to build the confidence interval. We just multiply, well, we use this formula right here. So we take S, the sample standard deviation, times the square root of the degrees of freedom, n minus 1, divided by the chi-square upper. Now, don't square anything here. This is chi-square is just referring to the x value from this distribution. So anyway, it's this number we stored as U, and so we do it just like this: 0.02 times the square root of 19 divided by U. Make sure, some of you may have to put parentheses around the 19 divided by U. Okay, and this gives us the 0.15 something. Okay, and that one is, that U there is the 32.8 something, which remember is what we got on this previous slide right here, And anyway, that turns out to be about 0.015. And then do the same thing, but replace this by L instead of U, where L is our 8.9, which we got from our inverse chi-square program over here. And that gives us our lower and upper when I round them off a little bit here. So we are 95% sure that the true population standard deviation is in this interval from 0.015 to 0.029. Now remember, just as always with any confidence interval, the population standard deviation in this case is some kind of fixed number. It's not moving around. What's moving around is if we do different samples of size 20, we're going to get different standard deviations, but we would still have this kind of an interval, and it would capture the true mean 95% of the time. Try another example. Suppose a manufacturer claims that the variance of the mass of a part manufactured is 3.4 grams. We want to test the claim that the sample of 30 items and compute their masses. We first convince ourselves that it's reasonable to assume that the distribution of masses is approximately very well by normal distribution. We measure the sample variance of the parts in the sample and find it is 4.2 grams. At a confidence level of 95%, is there sufficient evidence to say that the true variance is different from 3.4 grams? So now we're doing a hypothesis test rather than a confidence interval, but it is for variances. Okay, well, let's continue here. Here we want to use the chi-square distribution to test the sample variance from a sample to a given hypothesized population variance. This test is not built into the TI-84 calculator. You may look down the list and see a chi-squared test in your list, but this is another type of test that uses a chi-square distribution, and that will be covered in a later section of your text. That's the one that's built into your calculator, not the one we're doing here. So recall that we must know the distribution of individual measurements is normal for this test to work. The null hypothesis is that the population variance is equal to some known or assumed population variance, which in this case was 3.4 grams, and our sample S. So this is sigma. At least we hypothesize that sigma, and this down here at 4.2 is the S. As usual, we can have a left-tailed, right-tailed, or two-tailed alternative hypothesis. As usual, there are critical value and p-value approaches. So this is all just variations on a theme of what we've done earlier. Sufficient evidence to say that the true variance is different from. Different from indicates two-tailed. So we'll be using a two-tailed test this time. So here's what we have. Our null hypothesis is that sigma square is 3.4 grams, and our alternative is that sigma square is not 3.4 grams. N is 30. That's our sample size. That makes the degrees of freedom one less, which is 29. And our S square, our sample standard deviation, is 4.2. Certainly 4.2 is not the same as 3.4, but is it enough different that we have sufficient evidence to reject their claim? Well, we can do this a couple of different ways. Here is the way of doing this with a critical value method. So the this is the p-value method. This is the p-value method here. What we do is find our test statistic first. So our chi-square star, our test statistic, is n minus 1 times s squared over sigma squared. Now the sigma is the one that we go by the hypothesis, the null hypothesis. So that's 3.4. The s square is the one that we have from the sample, and those are variances. If these were standard deviations, we would have to go ahead and square them here. So these need to be variances at this point. And 29 was n minus 1, which is your degrees of freedom or sample size minus 1. So anyway, we work out this fraction on our calculator, and here it is done on calculator right here, and that's 35.82 something. That's our chi-square value. You could store that as x or something if you want. Now, what do we want to do for a p-value? Well, notice that our s square, our variance, sample variance, s square, is bigger than the hypothesized population variance. So what we do is we find the probability from that guy to the right, and then we're going to have to double it because it's a two-tailed test. So it's 2 times the probability that the chi-square would be greater than the one we got. So as always, the p-value is the probability of getting the statistic we got or something more extreme. Now, of course, we measure this with a chi-square distribution. There's a couple ways to do this. I could do this part by the chi-square, go from this value here, and then go to infinity, which I can't put in infinity, so I could put in something big like maybe 1,000, and then give it 29 degrees of freedom. Or I could do it the way that I did here, do 1 minus the chi-square from 0 up to this value, and this way you don't have to replace infinity with something. So anyway, this is what I did on the calculator, which you can see up here in the screenshot, and we get about 0.36. That's our p-value. That's a huge p-value, so definitely larger than our alpha, which was 0.1. So there is not enough evidence to reject the null hypothesis. We don't have enough evidence to say that they were incorrect when they made their claim. Now, some of this you can okay, if we wanted to do a critical value method, we need to do an inverse chi-square. So since we do have the inverse chi-square, we could find the critical values. So if we're going to do a critical value method, we need to split the alpha into 2 tails, since this is a 2-tailed test. So there's alpha to the left of our left critical value, lower critical value, and alpha to the right of our upper critical value. So if we have a critical level, or confidence level of 1 minus alpha, which is 0.95, then the alpha is 0.05, and then we have alpha over 2 is 0.025, and 1 minus alpha over 2 is 0.975. Or if you just say started with the alpha there, then you can get that. Now, the critical values then are going to be an inverse chi-square of this 0.025 with 29 degrees of freedom, because the sample size was 30, and then the inverse chi-square of this one here. Well, if you've got a Inspire, I believe that it has an inverse chi-square, but but we can make one. We made one with my program here, and so we can run this program, inverse chi-square. The left probability is 0.025, degrees of freedom is 29, and it returns approximately 16.05. And similarly, we do the same thing with the left probability of 0.975 to get the upper one, which is about 45.72. And so there we get our lower and upper ones. If you don't have the program, the way you would need to do it is over here on the right, graph the chi-square CDF, graph the horizontal lines at the two y values, which are cumulative probabilities to the left. Calculate those intersections here for the lower one here and the upper one here. And so those are our critical values. So anywhere between to the left of this or to the right of that one is going to be in the critical region. Now we compare that to our test statistic, which we computed on the last slide, and that's 35.8. That's clearly between these two. Between the two is in the non-rejection region. Do not reject, the non-critical region. So whether we're using the p-value approach, which is going to use just the chi-square CDF to find the p-value, or we're using the critical value approach, which is going to require us to do an inverse chi-square, either with a program or with this method over here, we get the same conclusion either way. Here we see some illustrations of this. I have graphed the chi-square PDF, and I have shaded here the alpha region. And the alpha here is, half of alpha is on here and half is here. That's your lower critical value of 16.05. This boundary right here on the critical region is your upper value of 45.72. The test statistic chi-square that we got was about 35.8. It's right here where this vertical line is. Clearly that's in the do not reject region. And if we wanted to find the probability of getting that or something further to the right, that's what we got shaded here. That is a chi-square CDF from that guy, lower at that same value, that 35.8 something, and upper is 1,000 this time. I did it a different way this time instead of 1 minus going from 0 up to that number like I did last time. And that gives you this region right here, but that's only half of your p-value because it's a two-tailed. Now we need an equal area over here on the left side, so we double that, and that's our p-value. Now, the good news here is that this can be automated. So guess what? Once again, I've written a program, and this program is for inferences about standard deviations. And this will automate the process of finding confidence intervals and performing hypothesis tests for standard deviations using a chi-square distribution. So with the addition of this program and maybe one more to the ones earlier in the slides and in the with the built-in programs, the TI-84 then can be set up to completely automate every confidence interval and hypothesis test needed for this the videos in this playlist, which is my last unit in my course. So anyway, here's the program. It's this one first, then go across like you read. So it's this one, then this one, this one, this one, this one. Then you go across the second row, and you go across the third row. So after this says interval, then it says for 1, and then sample, standard deviation, and so forth. So you can type all this in, and if you do, then this will work, and I'll show you it in action here in just a minute. And once again, if you can make it to the University of Arkansas Fort Smith campus, then I'd be happy to link this up with my calculator to your calculator and just get this downloaded very quickly so you don't have to type all this in. So let's put it to work here on an example. A weight loss program results in the following amounts of changes in weight in a sample of participants. All measurements are in pounds. We have some data. Test the hypothesis that the standard deviation of weight losses is more than 4. Use alpha as 0.1. Find a 90% confidence interval for the standard deviation of the weight losses. The first thing we have to do, and we cannot skip this step, we need to make sure that the population of individual changes in weight, not just the distribution of sample means, must be normally distributed. So the way we can do this is with the normal probability plot. We type our data in, L1. We've got to do that at some point anyway. Then we go to plot 1, turn it on, choose this last one here. Our data is in L1. Our data axis is we can actually choose X or Y, doesn't matter. And then mark it. Go down and do a zoom stat. And what you should see here is hopefully more or less close to a straight line. And they're pretty close to a straight line here, so we can assume that we can go ahead and work with this and keep going with this test. So we can also, well, we can actually run our program. It's going to do pretty much all of it for us. So we run our program called SD test for standard deviation test. And it tells us that it computes the hypothesis test and confidence interval for a one sample standard deviation from a normal population. And it asks us to enter the data list, which is L, and we tell it, we just type in L1, which is the second one, because that's where we have our data. It's going to return for us the sample standard deviation and the sample size. Actually, there's one screen that's going to show us before that. It's this one right here that says data, and it's either from a list or statistics. So we're going to choose list in this case, and we tell it which list we have our data in. You can also choose the stats version if you don't have the actual data, but you know the standard deviation and the sample size, and it'll prompt you to input S and N. So anyway, in this case, it figures out S and N. And then you have a choice between only an interval and a hypothesis test and a confidence interval. In this case, we want to do number 2. So the null hypothesis then is that sigma of x equals, well, you have to give it a value, which it stores as D, but it's 4. And then it returns the chi-square test statistic. And then you have a choice of doing a left, right, or two-tailed. And this one is... we said we want to see if it's more than, so we want a right-tailed, so we do number 2. At that point, you can either just type in 2 or move your cursor down and hit enter. And then it's going to return a p-value, 0.007. Notice that that is probably smaller than alpha. Let's see, it's not completely clear what alpha is here. Yeah, it is. There it is, 0.1. Okay, so 0.1 for alpha. So 0.007 is less than alpha, so there is enough evidence to conclude the standard deviation is more than 4. Well, anytime, especially when we reject the null hypothesis, we should always couple a hypothesis test with a confidence interval. So if we're going to use an alpha of 0.1, we need to use the same alpha for the confidence interval. So 1 minus that alpha is 90%. So we're constructing a 90% confidence interval. So we enter 0.9 when it asks us for the confidence level, and then it returns the confidence interval, approximately 4.46 to 7.97. So we're 90% sure that the true standard deviation of the population is somewhere between, say, 4.46 and 7.97. Notice in this case, I actually rounded down on the lower one and up on the upper one to be sure we got at least 90% in there. It would, in some cases, you might have just rounded this off, 4.47 and 7.9, still 7. Okay, so with that program, I think you can answer lots of cool stuff about confidence intervals and hypothesis testing for standard deviations.